Hello everyone, my name is Michael Rukowski. I'm the Technical Director at MetaMeow. This tutorial is a recap of the Houdini Ignite workshop in Seoul 2025. For those of you who haven't had a chance to attend, in this tutorial I'm going to take a practical, scalable and layered approach to creating destruction, which can be used in a variety of real-time projects and suitable for multi-platform games. Our references first, we set out to create a procedural building which resembles Japanese tower mansions, and then we went to fracture it and destroy it. Without further ado, let's hop into Houdini and create a file. I will first import our geometry, which you can see a model building here. And I'm just going to quickly press D to go into display options and change my background color into something that is easier to look at. I will also change the viewport shading to flat wire shading. And as you can see here, we have a reasonably detailed model without too much redundant geometry or too many subdivisions. We also have interior geometry such as walls and floors that can help add some extra detail into our fracturing simulation. If you look at the file, the number of vertices is at 1.4 million now, which is a little high poly. So first, before we start fracturing, we'll see what we can do to make that lighter. If I go into wireframe mode by pressing W and inspect the building, you can see there are some high poly details here, which are these metal bars. And also, as we talked in the beginning, we're not going to destroy the entire building. So in my case, I'm going to leave the entrance area untouched. First thing we're going to do is drop a delete sub and remove the items that we're not going to use. In this case, the entrance and the iron beams. As a result of that, we cut down the number of vertices to about 500,000, which is suitable for using with Vertex Animation Textures. I'm going to perform some basic cleanup before we go into Voronoi fracturing. We will also leave our low-res bounding box and scatter some points on it. In my case, I will just drop it to about 20, and I'll change the global C to something a little more pleasant on the eye. Create a Voronoi fracture sub and connect both items to get a basic fractured shape. We also need to output the primitive cell point attribute, which allows us to identify the pieces which are disconnected but part of the same cluster. To illustrate these, you can go and create an exploded view node, which by default separates every disconnected piece of geometry. In our case, we don't want to do that. We want to group different parts. Although they are a disconnected piece of geometry, they belong to one cluster. So we'll use this attribute as a point of reference for that. Next, we are going to fracture this same part again to create a layered destruction. So we'll create a for each loop and do almost the exact same thing. At this point, we have 20 pieces, and I want the overall number of pieces to be less than 100 to be a bit more manageable. So in my case, I will only create 4 pieces this time. Create another fracture and connect. We'll also output the primitive cell point, but override the name so that we can tell which parts are the major fracture and the secondary fracture. If we preview the for each end node, we can see the final result. However, as you can see here, the passes are more than expected, so I'm going to cancel and look into it. In the for each end node, we actually need to iterate over a piece attribute, and this is where this LPT comes in. So make sure we only have 20 iterations for each large piece, as opposed to iterating over every disconnected piece in this mesh. If we now create an exploded view again and use small cell PT, we'll get this kind of result. So you see pieces are more fractured. However, as you can see, there are some irregularities here, and not everything looks as we imagined. So I'm going to go into an attribute spreadsheet and see what's going on. We'll open our primitive attributes and look at the small cell PT. Small cell PT is from, if I sort it, goes from 0 to 3. However, what we expect is this number, which is 4, times this number, which is 20, the total should be 80 pieces. Why does this number go from 0 to 3 as opposed to 0 to 79? The reason for that is for every iteration we are creating this small cell PT. However, the Voronoi fracture node does not know about other iterations. That's why this number gets reset in every iteration, and all the pieces for each piece, every first, second, third, and fourth piece gets the same ID here. In order to prevent that, we'll create an attribute wrangle node and override the small cell PT with our own logic. So I'm going to take this number and one more number that is our iteration. And for this, we need to create a meta import node and connect it to the second input of the attribute wrangle. After doing this, we can read the detail attribute from the second input. Remember, this counts from 0, so 1 is the second input. We read the iteration attribute here. And the numbers are still not fixed because I need to iterate over primitives. Finally, if we look at small cell PT, the numbers are as expected. At this point, I'm going to create our first cache to save the result. Tick off time-dependent cache, hit save to disk in background and wait. In the next step, we are going to create convex pieces for our simulation. This is going to be the proxy simulation. One of the tricks that we can use to create faster iterations, especially important in games, is to do the simulation in low resolution and then transfer the simulation results to high resolution pieces. So for this, we're going to create our low resolution geometry first, and we will do it using the shrimp crab SOP. I will drop a fuse after this. And in the shrimp crab, we will preserve attributes and groups. Remember to reload the cache, as Houdini sometimes is not very smart at understanding when a cache is done. Okay, so we see there's too many iterations, and that's because the piece attribute needs to be specified. Okay, we'll iterate over small cell PT, and immediately we get this result, which is a nice convex representation of our mesh. This can also be created using a convex decomposition SOP. However, this is much slower, where a for each loop is much more efficient and controllable. Create another file cache to write out our convex holes. Save to disk in background. I'm also going to clean up the small parts here and going to start preparing the RVD simulation. We're going to measure the volume of each piece while iterating over small cell PT, saving it to density. We'll also promote our cell PT attribute from primitives to points. After promoting the cell PT attribute here, we are going to pack our geometry. We'll transfer some attributes, including the density, small cell PT, and cell PT. Now we are going to start creating constraints for our simulation. And this will be largely based on clusters with slightly larger radius. We get a constraint network like this. We're going to also configure our constraints with RBD constraints properties sub. Plug them in, as well as our geometry from earlier. Change the constraint type to hard. Now, as we get constraints, as you can see here, these are constraints connecting the small cells inside each cluster. So we are going to group those into small cell constraint group. And since we have small cell constraint, but we don't have the large cell constraints, we will add those as well. And we will use a different method for this. We'll extract the centroids and use the connect adjacent pieces sub in order to create the constraints. We'll use the adjacent points method and increase the search radius, as well as max search point, to get a nice clean network like this. We'll also configure this using RBD constraint properties, and we'll use glue constraints in this case. Connect it to the wrong input. Make sure to use the constraint geometry input. And sorry, I'm not clicking the right inputs. We need to group these constraints as our regular constraints and then merge them in together. Now we have a nice network of two types of constraints, and we are ready to configure our RBD simulation with the RBD configure sub. In our RBD configure sub, we are going to visualize active pieces, which we'll be using in a minute, and transfer some extra attributes, including the density, mass, and cell point. We're also going to tweak some options, enable active, which now, thanks to our visualization, we can see the active pieces in green, and we'll use bounce for this, which I will explain in a minute. We'll also use the acceleration and angular acceleration limits to prevent pieces from flying off too fast. We'll change the material type to brick and use user density of 1500 with some variety as well, and increase rotational stiffness. Now that our constraints are and simulation is almost set up, we'll also add a sphere, which we'll use this sphere to determine which parts of the building we want to collapse and which parts we want to keep as a static geometry. So I'm just going to place this sphere to roughly overlap with the right-hand side of the building and leave some of the bottom part untouched. We'll connect it to the fourth input, which is static bounce geometry on the RBD configure node, and offset it so that we just get enough of the geometry falling with some pieces untouched. With this done, I will create RBD bullet solver. If we hit play, nothing is happening. That's because we haven't set up our forces yet, and there are no collisions. But before that, I will quickly change a few of the settings here. Add some friction to our pieces, decrease the bounce. In collision, we'll add a ground plane with some friction and no bounce. In the forces, we'll enable drag and drag spin and increase the amount of drag. This prevents pieces from never losing energy as in space. We want to make sure that they feel heavy and slow down as they move. We'll create some break thresholds for both constraint groups. The first one is our main constraint group. This will use an angle threshold of 0.2 and the default distance threshold. The second constraint group will use small cell constraints and will break at a certain frame of 25, as well as have a distance threshold of 3. Finally, in the output, we are going to output some attributes. I'm just making sure this data that we need. We are ready to create our custom forces, so we'll jump into the RBD solver. Now we are ready to create our custom forces, so we'll jump into the RBD bullet solver and drop a pop wrangle SOP. Oh, I jumped it. We'll drop the pop wrangle SOP again. And in our pop wrangle SOP, we'll first create a random vector. Then what we will do is add random velocity and set our velocity to a certain number. This is adding a custom force, which after a while we want to fade out, so we'll only let it affect for the first 25 frames. Also add another pop wrangle with only the Y force, pulling pieces down in order to prevent them from jumping off too far. Now with these two, we can test our simulation results. You can see that the result is looking fairly nice. Of course, at any point in time, we can go in and tweak our active pieces to control how much of the building we want destroyed and how much of it should remain intact. This kind of low resolution proxy geometry approach allows for very fast iterations and be able to create art directed simulations much more easily than using the high resolution geometry directly. Okay, at this point I am pretty happy with the basic look of the sim, and I'm going to create a cache. This is the low-res cache before we apply our high-res pieces, which I'm going to create here back from our fracture cache, which was created here. And one thing that I'm going to have to add here is an enumeration of our pieces. So I'm going to quickly add it here as it was missing. We'll enumerate piece per small cell PET and measure the area. Oops. We'll also we'll delete very small pieces here. Keep by expression, the area is smaller than a certain amount. We removed some very small pieces. And we should still be looking at our large geometry here, our high-res geometry. And we're going to enumerate our pieces using an attribute wrangle. Here we'll use a very simple expression using the piece and convert small cell PT into an ASCII value. It might complain before it does. Let's cast it explicitly to an integer value. And now we end up with a name attribute as is here. We can take this geometry and triangulate it to prepare our pieces for export to Unreal Engine. We'll also use the facet SOP with unique points enabled to make sure normals information goes through. Finally, we will pack our pieces using the name attribute and making sure we transfer all attributes. Based on this, we can transform our pieces, which is a SOP, which can take our low-res sim and apply the results to the high-res geometry. For this, we will also need a third input, which is the rest points. And for this to work, we will use our cache here, which might need recaching now after we've done the enumerations. And actually, I will need to first cache the convex pieces. Meantime, I'm going to prepare our third input by simply time shifting everything to frame 1. So we'll take frame 1 of the low-res sim as the rest points for our cache, and then use the simulation points as the actual simulated output. Make sure to transfer our attributes. And before that, we can see some of the bits are missing. There are 72 pieces in this simulation, while we expected 80. Now, after reloading our caches, you can see we have 80 pieces again, so it was a matter of the caches being old. I'll double check the simulation result. It is looking fairly nice, except for a single piece that is kind of floating in the air, so I'm going to move our sphere slightly to the right. To make sure the static part of our building looks realistic. Okay. Recreate the cache. after reloading, we can see that the pieces look great. The information is fully transferred, and we can see our high-res geometry moving in the exact same way as our proxy geometry, which is a fantastic workflow for quick iterations, and also be able to control the amount of geometry we have in our caches. We'll finally create another file cache for the high-res geometry. Save to disk in background, and split our outputs based on the active attribute. The active attribute should be a point attribute in order to ensure it is read correctly. Now we are ready to prepare geometry for exporting into VAT. So we'll just delete some attributes that we do not need, and the ones we need are position, velocity, W, pivot, and orient, as well as our material path. This will be the VAT output, and on the right hand side we are going to merge our entrance back in, to create the static mesh geometry. Finally, we will unpack this, triangulate the entrance. The entrance is already triangulated, but just to double check. And delete some attributes that we don't need. In our case, we only need the position and normal, as well as, again, the material path. With this, we are ready to export a static FBX. I'll put it in the export folder. Give it a meaningful name. Make it easier to import into Unreal, and press save the disk. We're also going to export our VAT, and for this we'll go into Side Effects Labs. If you don't have this shelf, then press the plus button, go into Shelves, and select Side Effects Labs. And if you don't have Side Effects Labs installed, then go to Houdini Launcher and make sure it is installed through here. Okay, with this geometry ready, we'll go into Side Effects Labs and press the VAT button, which creates a new ROP here that I'm going to rename to something more meaningful and change the settings to prepare for rendering our geometry as well as textures out. First one we'll select is the input geometry. I'm going to use the rigid body dynamics at Unreal Engine. Geometry is cached. Increase texture size. We won't need colors, so we'll need keep geometry positions and rotations. And press render all. This operation takes a few minutes, so I'm going to wait a little bit and show you the final result. Our VAT cache has finished exporting, which took about 5 minutes on my machine. And now if we go into our a home directory with the hip file, go into export, find the name of our scene file. Then in the geometry folder, there should be an FBX file, and in the texture folder, there should be two textures, one for the position and one for the rotation of our pieces. These are two EXR files. This concludes the RVD part of our simulation, and now what I'm going to do is show you how to create the debris. So we're going to create another geometry, call it debris, jump inside and start creating our network. First we will merge in the geometry for our VAT as a starting point. We are going to unpack this and make sure to transfer the name attribute. From there, we will remove the unnecessary parts. We'll only use the concrete group, the concrete, as well as we need the roof, and we need the floors as well. We'll use these three layers to generate debris. We'll also create a time shift and clamp to both to ensure that our debris is created in the right place. Then we'll drop a trail SOP, which will be used to compute velocities. Now we'll create a debris source SOP, which is used to spawn little debris particles to be used for our simulation. Going to increase the density scale. And strangely enough, the pieces aren't moving, so I'm going to go back to see what is going on here. Yeah, the pieces start moving a little bit later, so we'll go back to see the result. We're starting to see some debris. So at this point, I'm going to cache the result. Debris source. And while this is happening, we'll also start filtering the results, as there are slightly too many points. We won't need all of them. We'll filter by the velocities. Delete points with less than 0.01 velocity. We'll also randomize a few attributes, starting from p-scale. And in here we're going to use a custom ramp. Create a shape which looks roughly like this. We'll create another randomize. Use it to control velocity. In this one we'll add a value from -1 to 1. Finally, we will also randomize the W, which will give our debris some orientation. In this case, we'll also add a value of 10 in both directions. Finally, we'll randomize the orient as well. Now we're going to filter these points even more. In this case, we'll remove random points, which will base on a threshold value. I'll press this button to expose our threshold. We'll make it just under 1. Now this creates still quite a lot of points, so I might increase it even more. So we only need about 100. Continue to randomize attributes. In this case, we'll go with class that will use a custom discrete string attribute. 3 values, so we'll have 3 variations of our debris. And we're going to add point velocity SOP. Add some curl noise. Also keep incoming velocities while adding the noise. Finally, we'll delete some unneeded attributes. The ones that are needed are W, descale, orient, velocity, and class. Finally, we're also going to assemble the result of our unpack to create packed primitives while transferring we'll configure RBD. Set these pieces to animated and deforming. For this will be our collider. And finally, we'll create a dot network to simulate our debris points. Connect these 2 outputs. And before we forget, create an output for our debris. For our debris, we're going to use a simple pop simulation. So we'll create a pop object, the pop source, pop interact, plug them in together with a gravity force. On the left hand side, we're going to merge our collider. Create a static solver. Merge with our particles and create a ground plane to merge. And this is the basic setup that we all need. The physical options will set bounce to 0, prevent our particles from jumping up and down. we'll use the first input as a source for our particles. And in birth, we're going to birth a constant rate of 5,000 particles in the first 24 frames. Now our simulation starts a little bit late, so I'm going to extend this to allow for more debris to spawn. And we end up with a nice number of simulation points for our debris. Now we are going to create our debris scatter pieces. For this, we'll just create a simple box, make it 10 in all axes, and immediately we're going to fracture it using the RBD material fracture SOP. For this, we are just going to use the default concrete pass with some edge detail and increase the noise height. And we end up with pieces like this. Which I'm then going to triangulate. The amount of detail is a little high, so I will increase the detail size and reduce our piece geometry to keep the poly count as low as possible. In this case, we'll drop it to 50%. We'll also scale down our pieces to more manageable size and assemble to prepare for copying to points. I'm going to create packed primitives, and then using attribute wrangle we will bring each piece to the origin. We end up with a collection of pieces which looks like this. In order to preview them, you can use the align and distribute SOP, which lays them out nicely. And as you can see, we have some nice looking rock shapes, which we'll enumerate. Using the name attribute and enumerate pieces with the debris ID. Now these instances are ready to use. We'll keep them in one box and this one in another. Finally, to combine these two together, we'll import our simulation. We'll use the pop object geometry. Create an attribute wrangle. We're going to override our debris ID. Create the file cache. From here, we're ready to copy our instances to points. Sorry, the first input should be our instances. And we are copying them to simulation points. So as you can see, these are copying almost nicely, except we get a whole bunch instead of only the points that we needed. Now it's looking much better. Due to how our simulation is done, you will see that the number of points is not constant throughout the simulation. This will create issues later down the line when we try to export this as a VAT cache. So what we need to do is to use a technique called object pooling, which means we will create the constant number of points and then reuse this constant number of points to move them to their position when the particles are generated. So the points, the maximum number of points will always exist, but it will be hidden away in a place where no one can see them until they are needed, when they are transformed to their final position. I'm going to add this now. Going to time shift to the final frame. And we're going to adjust an attribute. And for this, we'll use the p-scale to create a random value. Then we'll move everything back to the origin again. See, what we should be doing is using this cache instead of our uncached result. And now all the pieces are transformed here, so you can see throughout the sim we always have the constant number of 5,832 points. we're going to just copy the attributes back. And then copy positions. Take the key, the scale, as well as the pivot for my first input. And finally, we can use this as our template to copy to. And with this setup, we are ready to export Vertex Animation Texture cache. I was just looking at the result of the cache and wondering why these points aren't moving. And the reason for that is in our DOP network, I have not ticked one box that is necessary, and that in the static object we want to use the forming geometry. This allows the DOP network to recognize how the moving pieces of the building are affecting the simulation, and is necessary for our DOP sim to work correctly. So with this selected, I'm going to resimulate the debris point sim again and recreate our cache. After this cache is done, we're going to cache it one more time, and this will be our final sim debris. This is ready to turn into an output, ready for VAT export. While we are waiting for this sim to finish, I'm going to set up the VAT for the debris. So hit the VAT button again, press N, and go to ROPs. We'll create another ROP node just for the debris. The debris will use very similar settings to the tower mansion. We'll just point it to a different geometry. Add debris VAT. The rest will just increase the texture size, as well as remove colors from our export, as they are not necessary. And with this, we are basically ready to export. However, still waiting for the simulation results, so give it a little longer. And as you can see here, compared to the previous sim, which had some static points here stuck inside the collider, the simulation is much smoother. And we can see it together with our high-res building. Or if we want faster feedback, we can look at our proxy geometry. We can start to see this very nice layered effect of the debris, the large pieces, and then the debris layered on top of it. And you may notice at this point, once we copy the rotations over, that the particles seem to always spin. And that's because of another issue in the dot network, which is enabling auto-sleep on our particles. Also increase the velocity threshold. And with this result, I will simulate one more time. Okay, if we run the simulation right now, you may notice that the collisions calculation is on the slow side. And there is one more technique that you can use to optimize that if you are feeling impatient, and I'm going to show you how to implement that. So right now, we are using RBD collisions through RBD configure here. This part, we don't actually need to set it up like this. We can use volume collisions, which will speed things up considerably. I'm going to show you how to use that. So create a VDB from polygons. And increase the voxel size. And based on this, we can plug it in to the second input. Actually, that's not even necessary. We can just create an output here. Call it out debris SDF. Okay, this is all that's necessary in the SOP side. And let's jump into our DOP network and optimize this as well. So instead of using a static solver here, we can plug it in to the pop solver directly. We can just merge them. At this level, plug it into object. This is the first change. The second change we need to make is now we are not using RBD collisions anymore. So we will change the SOP path in the static object 1 to out debris SDF. We'll leave use deforming geometry ticked, as that is necessary for deforming collisions. And in the collisions tab under RBD solver, we're going to change collision detection from use solver default to use volume collisions. We'll also change the mode from ray intersect to volume sample. And this is all we need to do in this rollout. With this, I will go out of the simulation and press play to see the results. As you can see, the collision results are much faster now and don't take only a fraction of time to calculate compared to RBD collisions. So based on this, we can go back to our debris sim cache, hit save to disk in background, and recreate our cache. Okay, as our cache is ready again, I will go to review the results. As we can see, the pieces once fall on the ground, they stop and they don't roll forever, which is the result that we expect. So with this, I can create a final cache, hit save to disk in background, and wait until this is done. So it will be fairly quick. Now we are done with the geometry cache, and we'll hop into ROPS to create our debris VAT data. And we are having an error, so have to go back to see what is going on. And as we can see, there is no pivot or orient data that is required by the AT. So we'll need to trace back to find where this data disappeared. You can see at this point, orient is still here. Here we have orient and pivot, and in copy to points, this disappears. So in this case, we'll have to go in and make sure that we copy 2 points by copying pivot and orient. And after explicitly specifying these, we can find these attributes present. So with this, we'll recache the result. Again, this does not take long because we have a previous DOP cache. If you haven't made one, then this process will take much longer. And in the ROPs, we can now hit render again and see the result. Okay, our cache is done again, and we can see 2 more files here. These are much larger. That's because simply the number of pieces is much larger than before. Since we finished the building RBD simulation as well, the debris, in the final part of the Houdini simulation, well, we're going to add smoke to our simulation. Add a new geometry, and we're going to merge in first of all our low-res simulation, and it appears that we may not have it as an output, so I'll first add that in. We're going to to unpack this first. And again, same as debris, we'll use debris source to create some initial points. We'll also limit the number of points to 100,000. And we're going to manipulate density using an attribute wrangle. Our density will be controlled by a ramp and age of the debris. Now this is a ramp. We're going to create a hill. Now we need to compute velocity using the trail SOP. We'll use the forward distance for this. And now, with another attribute wrangle, we're going to set the velocities. We'll normalize our velocities. We also store the length of our velocities as a separate attribute. And finally, create a temperature attribute. This will be our pyro fields. We'll also reduce the number of points. Make sure we delete points. we'll add some noise to the temperature. As well as the density. In our case, we're going to use a multiply operation and use a ramp. So the vectors will use floats here. We're going to use the volume rasterize attributes to create some volumes for use with a pyro solver. For this, we'll use the density, the temperature, as well as the velocity field. So create a source attribute. And then we're going to use the velocity blur function with a negative shutter offset. This creates a kind of smoke trail, which we can use as volume sources for our sim. And I'm going to cache at this point. We also need a collider for our simulation. So I'll take the first unpack. So going to unpack. So going to create a trail, compute velocity, forward distance. This time we won't change anything else. And with an attribute wrangle, set the density to a constant value. Now based on this, we can create a VDB, which is a faster way of evaluating collisions. Bump up the voxel size. Also create some surface attributes. First one will be D, and this will be encoded as velocity. And then we'll also keep the density here and make it the collision VDB. For this we can use the default. And then based on this, we'll create another file cache, which becomes the volume collision. Now with these two running together, while we are waiting for the results, I'm going to create a pyro solver and plug in both our sources and collision geometry. And I'm going to set up the pyro solver settings first. In collision, since we are not using geometry, we are using volume collisions. We'll set this to SDF volume velocity. In the ground plane, we'll set it to close below 0. In the sourcing, we have a number of fields. The velocity on the right frame. We'll also create some movement in dissipation. From 0.01 to 0.1 throughout the length of our animation. We'll also use buoyancy. And the reference temperature in Kelvin will drop down right down. Also add some turbulence. And that is pretty much all we need to set up at this point. One thing I missed is the wind. Ensure that wind is set up. And we are almost ready to begin. And we can see our smoke, which spreads in quite a billowy way. And while we are waiting for the volume sources to finish caching, I'm going to prepare the smoke for export. So we are only going to keep the density field. Also create a pyropose process. And in this node, we'll convert it to VDB. And finally, we can use a file cache. Instead of BGO, we'll use VDB. And here we are, we created the smoke. So before our caches are ready, we can press save to disk in background. And watch our cache files appearing here in the folder. Okay, our caches are now done, and we have 3 or 4 layers of destruction here. The first one is the large pieces, then we have a second breakup into smaller pieces, then we have debris which follows through with different scales and rotations that is simulated separately. And then finally we have a smoke layer on top of it to add to the realism of the scene. Once again, this setup allows us to separate the number of pieces from our geometry, which means we can have a very detailed building model and then slice it into just a number of pieces, or we can control the exact number of pieces that we want. And if we want to, for example, separate the glasses and make them fall all separately like in feature film, we can also do that combined with this approach by just simulating them on top of our large clusters. So this approach does not mean we cannot have a very detailed, very granular simulations. It just gives us a more flexible, faster way of iterating, which is both are directable and scalable for different platforms. With that said, in the next part, the second part of this tutorial, we are going to bring all of this data into Unreal Engine and make sure this plays back nicely. So I will see you in the second part of this video. Thank you.